In the summer of 2025, the United States Department of Energy made a purchase. 3 liters of a substance called helium-3. That sounds completely unremarkable until you understand what it was. It was the first time any government in human history had purchased a resource from beyond Earth. The helium-3 came from the moon, and the DOE bought it not because fusion energy is here yet, it isn't, but because they needed to signal something. That the race to control what may be the most valuable energy resource in the solar system had moved from theory into procurement. Right now, at least 4 countries and multiple private companies are positioning themselves to mine the moon. Not for gold, not for rare metals. For a gas so rare on Earth that the entire global supply fits inside a single room, but so abundant on the moon that scientists believe it could power human civilization cleanly, without waste, for 10,000 years. Here is what helium-3 actually is, why it's up there and not down here, and why the next 50 years of global energy and global power may be decided on the lunar surface. What helium-3 is and why it matters. Most people know helium as the gas in birthday balloons. Helium-3 is not that. It is a rare isotope, chemically similar to regular helium but with 1 fewer neutron. That single structural difference makes it one of the most useful substances in advanced physics. Today, helium-3 is already used in medical imaging, in specialized detectors, and most critically, in dilution refrigerators, the machines that cool quantum computers to temperatures near absolute zero. Companies building quantum infrastructure are already signing long-term contracts to secure future supply. A Finnish company called Bluefors has committed to purchasing 10,000 liters per year once lunar production is viable. Microsoft and other quantum players are lining up similar arrangements. But the application that changes everything is fusion energy. Nuclear fusion, the process that powers the sun, releases enormous amounts of energy. The problem with most fusion fuel combinations is that they produce radioactive neutrons, which means radioactive waste and infrastructure challenges. Helium-3 fused with deuterium, a common hydrogen isotope, produces clean energy. No radioactive byproducts, no long-term waste, just helium gas and power. The physics works, the engineering remains unsolved, and fusion using helium-3 is harder to achieve than conventional fusion approaches. But the potential is clear enough that governments are spending real money to secure supply before the technology arrives. The problem is where helium-3 comes from, or more precisely, where it doesn't. Why the moon has it and Earth doesn't. The sun constantly emits helium-3 as part of the solar wind, a continuous stream of charged particles that radiates outward through the solar system. Earth is protected from most of this by 2 things: its thick atmosphere and its magnetic field. These shields deflect the incoming solar wind before it reaches the surface. As a result, Earth has accumulated almost none of it. Total global supply of extractable helium-3 on Earth, approximately 15 to 20 metric tons. That's the entire planetary reserve. The moon has no magnetic field, no thick atmosphere. For 4 billion years, it has been absorbing solar wind directly, accumulating helium-3 in the top layers of its soil, the regolith, at concentrations roughly 100 times higher than what exists on Earth. Estimates of total lunar helium-3, approximately 1 million metric tons. To put that in energy terms, 25 tons of helium-3, a quantity that could fit in the cargo bay of a large rocket, could theoretically power the entire United States for a year. The full lunar reserve, if fusion technology reaches viability, could power human civilization as we currently know it for over 10,000 years. The substance is sitting on the surface of an object 240,000 miles away, and it has been sitting there since before humans existed. The race that has already started. The geopolitics of this have been moving faster than most people realize. China's Chang'e 5 mission in 2020 returned lunar samples to Earth, the first samples brought back from the Moon in 44 years. Scientists at the Chinese National Space Administration measured and characterized helium-3 content in those samples. In 2022, they discovered a new lunar mineral called changesite, a tiny crystal 1/10 the width of a human hair, that contains helium-3 in its structure. China is not waiting. Its Chang'e 6 mission in 2024 returned the first-ever samples from the Moon's far side, a region continuously exposed to solar wind and potentially richer in helium-3 concentrations. Chang'e 7 and Chang'e 8, scheduled later this decade, are explicitly targeting the lunar South Pole, a region believed to contain both water ice and helium-3 deposits. Chang'e 8 is specifically designed to demonstrate in situ resource utilization, extracting and using lunar materials on site. By 2035, China plans a permanent international lunar research station at the South Pole, built in partnership with Russia. In August 2024, Chinese scientists published a proposal for an electromagnetic launch system on the lunar surface, a rotating arm that would fling extracted materials back toward Earth at a fraction of current rocket costs. On the American side, a Seattle-based startup called Interloon, founded by former NASA engineer Rob Meyerson, has secured $18 million in funding and is preparing its first hardware deployment. Its helium-3 mapping camera, mounted on Astrolab's Flex rover, is scheduled to land near the Moon's South Pole in 2025 to identify the highest concentration deposits. The DOE purchase in mid-2025 was not symbolic. It was strategic, a signal that Washington intends to be part of this supply chain. The technical problem. None of this is simple. The helium-3 in lunar regolith is not sitting in pockets, waiting to be scooped up. It is distributed through the soil at concentrations of roughly 10 to 20 parts per billion by mass. To extract 1 gram of helium-3, you need to process hundreds of tons of lunar soil. That requires industrial-scale machinery operating in a vacuum, in temperature swings from 250 degrees Fahrenheit in sunlight to minus 280 at night, in soil made of particles sharper than glass that destroy equipment seals and damage anything mechanical. When Apollo astronauts brought lunar dust into their landers, it triggered immediate respiratory irritation. They described the smell as burnt gunpowder. The dust is electrostatically charged, hyper-abrasive, and adheres to everything it contacts. It damaged spacesuit boots and container seals on missions that lasted days. An industrial mining operation would need to function for years. Interloon has been running subscale excavator tests on Earth since late 2024. The basic approach involves heating the regolith to release trapped gases, then capturing and processing the vapor before it escapes into vacuum. It works in controlled tests. The lunar surface is not a controlled test. The engineering gap between current capability and industrial-scale lunar mining is significant, and honest scientists say so. But the commercial and strategic pressure to close that gap has never been higher. The geopolitical dimension. The 1967 Outer Space Treaty prohibits any nation from claiming sovereignty over the Moon or any other celestial body. But it says almost nothing about the resources on those bodies. This legal ambiguity is not academic. China currently controls approximately 90% of global rare earth mineral supply, a position it built over decades that now gives it substantial leverage in electronics, defense technology, and clean energy manufacturing. Analysts who study space resources describe helium-3 as a potential repeat scenario. Whoever secures dominant extraction and supply chain position on the Moon may hold leverage over fusion energy and quantum computing infrastructure in the same way. The Artemis Accords, a U.S.-led international framework that has now been signed by more than 40 nations, establish principles for responsible lunar resource use. China and Russia have not signed. The two countries are building their own coalition for the International Lunar Research Station, a competing framework. What is emerging, quietly, and without much mainstream coverage, is a bifurcation of the lunar economy along the same lines as the terrestrial geopolitical divide. The Moon is 240,000 miles away. The competition for what it contains is happening here, now, on Earth. Here is the honest summary of where things stand. Fusion energy using helium-3 does not exist yet. The engineering to achieve controlled helium-3 fusion at commercial scale remains unsolved. The extraction infrastructure for industrial-scale lunar mining does not exist yet. None of that has stopped governments from spending real money, positioning missions, and competing for strategic footholds on the lunar surface. Because the sequence of events that matters is not fusion works, so let's mine the Moon. It is fusion will eventually work, and whoever controls the supply when it does will control something more consequential than oil. The U.S. Department of Energy has made the first purchase of an extraterrestrial resource in human history. China has returned the first lunar samples from the Moon's far side and has a permanent base planned for the South Pole by 2035. A startup in Seattle is preparing to land the first helium-3 mapping camera on the lunar surface this year. The Moon has been sitting 240,000 miles away for 4 billion years, absorbing energy from the Sun, storing it in the soil, waiting. The question is not whether someone will eventually come to collect it. The question is, who gets there first? And what kind of world that creates?